All right, we are back. Let's continue from where we left off, unless there are other questions about pumping lemma. Well, let's see. Let's think about what the pumping lemma really says. It says that L is regular, or if L is regular, then stuff is true. Right? That's what the lemma says. We must have L be regular first, then we can say, yeah, there is this pumping constant P, and then for all W, whatever. So if I wanted to prove that L is not regular, how can I use this idea to help me? Yeah, if the conditions do not hold, what does that tell me? L is not regular. And why is that true? Yeah, it's just the contrapositive of the first statement. And contrapositives of any statement are logically the same as the original statement. So negating the conclusion implies the negation of the supposition. So if we were able to show that if we have the conditions be not true, then we must have L is not regular. Because if it were, then the conditions would be true. Well, let's think about this. So here are the steps to show L is not regular. So we're going to approach this contrapositive from the original, and then eventually get the contrapositive, which sounds weird, but it makes total sense when we start thinking about it. Well, if you didn't know how to prove that L is not regular, what other method might you try? Contradiction, right? If we try to assume that L is regular, then if we're able to show in all possible cases that L or that the conditions are not true, then our supposition was wrong. So therefore, L couldn't have been regular to start with. So the first step is assume L is regular. Then by the pumping lemma, which is true, so on the midterm, do not say that the pumping lemma is not true, or the pumping lemma reached a contradiction, because the pumping lemma is true. The statement has reached a conclusion, or the supposition reached a contradiction. So if we know L is regular by the pumping lemma, what do we know immediately? There is this pumping constant P for L. So there exists a pumping constant P for L. What did the pumping lemma say next? Well, I think it said for every single string in the language with length at least this number P, then conditions. What if I found one string that violated those conditions? Would the for all statement be still true? No, because we just found one that contradicted that for all statement. So pick a string W in L with length at least P, and I'm going to put intelligently. Why do I put intelligently there? Because I wish I could tell you that there's this tried and tested method that will always work in every possible case of picking a string. There isn't, unfortunately. But when we're going to be doing some examples, you'll start to see patterns. And a common pattern is, since the repeated part must be within the first P characters, make all the first P characters exactly the same. So that when we are trying to pump in additional Y's into the string, you're going to only be pumping that particular character. And we'll see examples of that. But the whole choicing of the particular string, there's no tried and tested method, sadly. All right, but if we do pick a string that has those two properties, well, here's another thing. Can I pick a string not in the language? No. Can I pick a string of length less than p? No. A surprising number of people on past tests did either one or both of those incorrectly. If you pick a string that's not in the language or has length not greater than or equal to p, then you can't say anything about the other strings in that language. You can if you do both of them. So you have to pick a string in the language and has length at least p. All right, well, we said that once we look at this particular string w, what else has to happen in terms of this x, y, z thing? Yeah, well, how many ways are there for w to be written as x, y, z? We said that there is some way to write w as x, y, z. There's at least one way that works so that we can pump in the additional y's and all that. But if I'm able to show you that this particular w, this one w that I pick, has no way to pump correctly, then what can I conclude? That it can't be regular because we must stipulate that every choice of w pumps correctly. But if we can pick one that pumps incorrectly, i.e. pumps to where you get a string that's not in the language, then you're all good. So, want to show there is no way to write w as x, y, z so that, with length of y at least 1 and x, y not being too long, being length at most p. And like I just said, we want to show that there is a way to pump so that the for all statement about the i's at the end, such that x, y to the I, z is in L for all I, we want to show that there's no way for a particular I to stay in the language. Okay? So we want to show that there's no way for this to happen and that this satisfies x, y to the I, z in L for all I. And the way we accomplish this is pick a value of I and show that all decompositions of x, y to the I, z have it being not in L. So let's just recap for a sec. We want to assume that it's regular, the language is regular. Then there's this pumping constant by the Lemma statement. Then if we can show that there's this at least one bad string, then we can know for sure that this language could not possibly be regular. So how do we show that this string is bad? Well, we said that there is some way to write it as these three parts, but if we show there's no way to write it in those three parts, and therefore we would have some number of pumps of y being eventually not in the language. And we said that it's always in the language, but if we show that a particular value of I lands us out of the language, then this for all I at least 0 is violated. This condition is violated, and then therefore this language could not have possibly been regular. Questions before we do an example? So let's do that example that we had earlier. So let's let L1 be the set of all strings in 0, 1 star such that W has the same number of zeros and ones, and I claim L1 is not regular. Okay. So how can I prove this? Yep. So let's assume L1 is regular. Assume it's regular. What does that immediately tell me here? There's a DFA and, in this case, there's a pumping constant P for L1. Exists a pumping constant P for L1. Okay, we know that there's this pumping constant P for L1. Now what do I do? Pick some string with what two properties? It better be in the language, okay, and it has length at least P. Okay, well, there are many strings of that form. So I'm gonna pick a bad string right now. And I'm gonna pick 0011. It has the same number of zeros and ones, but why can I not pick this string? How do I know it has length at least P? I don't. I know P is a constant. It may be 10 trillion, it may be 1. I don't know what the value of P is. So I can't pick the string because I don't know it has length at least P for sure. Let me pick another bad string. So let's pick 0 to the P 1. And we note that it has P plus 1 characters, and therefore that has length at least P. So we're good, right? No, why are we not good? It's not in the language. All right, so let's try to pick a good string, or a better string, I guess. Any guesses or any choices? 0 to the P, 1 to the P sounds like a good choice. Intuitively, why should I pick? Oh, you had a question, sorry.
Could you say one more time why 0011 is a bad string?
It's a bad string because I don't know if it has length at least P. It may, it might not, but I can't guarantee that. Whereas like with the second one, it definitely has length at least P, but I don't know, it's not in the language for sure. Other questions? Okay. Intuitively, why should I pick 0 to the P, 1 to the P? It has these P zeros at the beginning, right? Where am I going to pump? In the 0 part only. Oh, if I put in another copy of Y, am I going to get this same string back, or am I going to put more characters in? More characters in. Y consists of what character? Zeros only, because it's within the 0 part. So I'm going to put more zeros in. Did I change the ones? No. So could it stay in the language? No.
Did you choose to make Y part of 0 because XY?
It's length at most P. Yeah. That, I'm just going to note, you definitely should use this condition, but the condition XY has length at most P is not necessary for the pumping lemma. You can actually prove a version of the pumping lemma which avoids that condition, but it's so much easier here because if we didn't, then if we look at this string, instead of saying that, okay, yeah, the y part is right here, I need to handle all possible cases. It may be the case that y straddles the middle or it's over here. I don't know. And I need to handle every one of those cases. But by saying that's within the first p characters, it dramatically reduces the number of cases I need to look at. Okay, so it makes our lives a lot easier. Okay, any other questions? Yeah.
Why would we be able to do it with one?
What do you mean do it with the one?
So you're saying you're going to be adding zeros. Could you not do the same with the one?
Because I know that xy has length at most p, and that's a prefix of the string. And so therefore the first p characters are zeros, and therefore y can't extend past the zeros. So that's why, yeah.
But you're just assuming that y is within the first p.
It has to be, yeah. Because I assume this p constant exists.
But
Yeah.
since that rule is optional, could you potentially do it?
But then you need to handle every single case. Yeah, and you could, but it's just, yeah. Other questions? Yeah.
Yeah, so how does that prove that one more time?
We're going to prove it in a
Okay,
second.
we haven't.
We have not formally proven it, but that's just an intuitive idea.
Okay.
Since y is in the zero part only, then if I stick in another copy of y, I've added some number of zeros to the string. I don't know, because I need to handle every case. But I added at least one, because y's length is at least one. So therefore, I'm going to increase the number of zeros by one, but I'm not going to ever touch the number of ones. And so therefore, it can't be in the language of equal numbers of zeros and ones. Okay? Other questions? All right, so let's formally prove this. Well, since y must be in the zeros, where must x be? In the zeros. Do I know how many zeros x or y has?
No.
No. Because I need to handle every decomposition. Well, I know every decomposition puts x and y in the zeros somewhere. Okay? So we can see that. And so now we're going to let x be some arbitrary number of zeros. So we're going to let x be some number of zeros. Let's say that there are a of them. And what do we know about this value a? Could a be 0 here? Yes. Could x be the empty string? Yep. So a is at least 0. This one condition, a at least 0, will not actually be necessary, but gets us in the mindset of thinking how long our strings are going to be. But the next one will actually be important. Well, I don't know how many zeros y is. It may be the same number as x. It may be a completely different number. So let's say that it has b zeros in general. What do we know about b? It's at least 1. I don't know about anything about the length of xy other than it's at most p characters. It may be much less. It may be all p, but I know it's at most p characters. So we're not going to actually use the upper bound here. We may in a later problem. Oh, not 0. 1. 3 years of recitations, that's the first time I made that mistake. Yeah.
So will z in this case continue to 0?
Maybe. Maybe. We'll see. But is z the rest of the string after the x and y part? Okay. So if it's the rest of the string, how many zeros must it have? Well, we started off with p of them. The x part took a of them away. The y part took b of them away. How many zeros do I have left? P minus a minus b.
You shouldn't have any zeros, right?
Potentially. All I know is that x and y together have length at most p. It may be all p, but it may be much less. But so I'm handling every decomposition here. So implicitly, this is not necessary, but a plus b is at most p, because x and y together can't have more than p characters. Is that all of z? and it has all the ones left over. Okay? So I'm handling every decomposition right here. I'm saying x is some number of zeros, y is some possibly other number of zeros, and z is the rest of the string. What must I do, or must we do now? Well, we said that for the pumping lemma part, it said that for all I, if I put in I copies of y into the string, it'll always stay in the language. What is our goal here? Well, we got to find some value of I that gets out of the language. It said in the lemma that every single value of I works. But if we find one that doesn't work, then we violated the condition. And then therefore it's not regular. What value of I should I not pick here? Always. What? We can actually pick 0, and we'll see that. Which one should I not pick? 1. Why should I not pick 1? It's always in the language. We chose, that's the original string W, X, Y, Z. It's the original string, and we guaranteed it's in the language. A string in the language will never not be in the language, unless it's kicked out. We better not pick I to be 1, so in other words, one choice of Y, because that's the original string here. We have exactly one copy of Y. So we better pick something other than 1. And it'll actually turn out any value other than 1 works. So, any choice? 2. Let's actually do 2 and 0. So, but do I need to prove both of them? No, I just need one of them to get out of the language. So, what is the string x with 2 copies of y, z? And we usually call that y squared, but it just means 2 copies of y. Well, let's just copy down our decomposition. So the x part is a zeros. 2 copies of y gives us how many zeros?
0, 0, 0.
2 b zeros. There. And then the z part, which is p minus a minus b zeros, followed by all the ones. I don't know about you, but I don't, yeah, go ahead. No, because I'm putting, in other words, I'm putting b zeros into the string. I'm inserting another copy of y into the string, right adjacent to where the y was before. Okay? The z part I never touched. The only thing that I really changed, quote unquote, is I put in another copy of y. So I'm getting a completely different string here. But I'm just copying and pasting the original 3 parts that I had. Okay? Other questions? Well, I don't know about you, but I don't like seeing 3 runs of zeros. Let's put them together. Well, if we have a zeros right here, and then we subtract a zeros, I hope a minus a is 0. So this a goes away. If I have 2 b zeros, and then I took b more away from them, then I have 1 b left. So at the end of the day, when all the dust settles, how many zeros do I have? P plus b. And how many ones? Just p of them, because I never touched them. What is the only way that that string at the end could possibly be in the language? If b is 0. But can b be 0? No. So therefore, I just violated the last condition, which means my original supposition that L1 was regular is wrong. And then therefore I can claim what? It's not regular. Okay?
You have to state that it is a computation at some point.
Yes.
You do?
Yeah. What was your question, sorry? because b was the length of y, and we made sure that b was at least 1 because we know y's length is at least 1. Mhm. Yeah.
So, how do you answer? Therefore, b equals 0. This is a contradiction, right? It's not really.
Yep. Question over here.
You chose an example string to be x, y, z, where x and y are both less than p,
Mhm.
x and y are less than p.
Yep.
And then therefore you chose a z to have, number of zeros is p minus a minus b. That's always length.
Well, the original input we chose was p zeros. So we had p zeros. The x part took a of them. A y part took some number b away from them. And then z had to be the rest of them because it's the rest of the string. Yeah.
So this is this like the formal way you want to say it?
Yes. Hmm. Exactly. Yeah.
So if you were to like write out, it contradicts the length of y is greater than or equal to 1.
Yeah. So you can actually just say here a contradiction.
Okay.
That's enough. Because we're assumed to know b is at least 1 here because we wrote it.
And you're saying this, the category of this is not proof by contradiction?
That this is a proof by contradiction because we assume that L1 is not regular, and in all possible cases, since we handled all possible decompositions, we got a contradiction in every one. We wrote it as though it was one case, but we actually handled a whole bunch of them at the same time. Other questions? So let's do the same thing, but for I equals 0. So x, y to the 0, z, and as we noted, that's just xz. But that's just a zeros followed by p minus a minus b zeros, 1 to the p. So it's just copying down our pieces again. What do these zeros resolve to? P minus b and 1 to the p after. And this implies what? A b is 0 and contradiction again. So sometimes it's not the case that every single value of I works. As long as you show at least one value of I that quote unquote works, that's enough. Okay? We happen to prove 2, which is fine, but one of them is actually sufficient. There are some languages that we can actually get to where there's exactly one value of I that works. But it's enough because we need at least one. But any questions of that example? Okay, I have 4 more examples. I don't know if we can hit them all, but I hope we can. All right, so let's do this one. So very similar language, but it's ordered a little differently. So we're going to use this language a whole bunch of times in this class for different reasons. So, and I claim that this is not regular either. So I'm going to show you a different method of proving that this is not regular. You definitely could go through the exact same proof as before, exactly the same. Like literally no changes other than substituting L1 for L2. It'll work exactly the same way. Because we chose the string 0 to the p, 1 to the p, is 0 to the p, 1 to the p in this language? Yeah, does it have length at least p? Yeah, and we'll actually get the exact same conclusion to if we proceeded that route. So I think that's kind of boring. But let's prove it a different way. Can you relate L1 and L2 together? Same number of zeros and ones from L1, and this one where they have the same number of zeros and ones, but they're ordered in a certain way. Could you relate them together? One's a subset of the other, but if something's a subset of a regular language, is it a regular language? You sure about that? Is L1 a subset of sigma star? Yeah. Is sigma star regular? Is L1 regular? No. So the subset of relation doesn't hold, regular languages are not closed under subset, unfortunately. So just because L2 it actually is a subset of L1, I can't prove anything based on that. But let's try this other idea. Well, how can I get from L1 to L2? Well, what I could do is I can extract the strings that I want, such that the strings that I want out of L1 are L2. And then we can maybe say something about that. Well, what about L1 intersect 0 star 1 star? What are the strings in that resulting language, whatever it is? Well, let's just be sure. L1 says that it's the same number of zeros and ones. All the strings that happen to have the same number of zeros and ones, even the ones where it's not of the form 0 to the n, 1 to the n. And I intersect it with, it must start with some number of zeros, followed by some number of ones. What strings have the same number of zeros and ones and are of the form zeros followed by ones? 0 to the n, 1 to the n. So this is equal to L2. I actually can't prove it this way. Well, yeah, you'll see in a second. I did the conclusion backwards. So, well, we know that L2 is not regular because we can do exactly the same proof as before. But suppose we didn't know. We did, no, that should be right. Yeah, that should be right, the way I did it. So it's L1 intersect 0 star 1 star. That definitely equals L2. Oh, okay. Yeah. So what do we know whether 0 star 1 star is regular or not? Is it regular or not? Yeah, because it is a regex. And we prove that they're equivalent to the regular languages. So we know that this guy's regular. Here's a proof that this shouldn't work. Yeah, this is not a valid proof. So,
Prove the L2 is equal to L1, then,
well, they're not equal though. What I wanted to say is that if L2, if L1 were regular, then what can I say about L2 in this case? Then what is regular? L2. Why is that true? Close under intersection. But we know that L2 is not regular. Yeah, so yeah, the conclusion's backwards. So, but here I can actually say something important. L2 is not regular, so therefore I can claim what? L1 couldn't have been regular.
so you can do it the other way.
Yeah, I can do it the other way around. Yeah. I don't know why. I thought that would work.
So that's applied by contrapositive.
Yeah, approved by contrapositive, yeah. Yeah, I was supposed to do the other way around, but yeah. So this is a really nice technique where you use closure properties to actually prove something that is not regular. Because if you assume that the two things on the left side are regular, then closure gets you to say that the thing on the right side is regular. Yeah. I can't because that's not necessarily true. That's not true because L2 intersect 0 star 1 star is not equal to L1. Yeah. Yeah. So I did those two languages backwards.
So that would be a corollary of what we're about.
Yes. Yeah. Yeah. So I was supposed to do 0dn, 1dn first. Then we would say that if L1 was regular, then L2 is regular. But if we prove that first, then we know L2 is not regular, so there's no possible way that L1 could have been regular, because if it were, then it would have been regular. Okay, so it's just using closure properties, intersection in this case, to prove that a language is not regular. Okay, sorry for the unpreparedness. But any questions about that, though?
So just to reiterate, you're really just proving that the first language we looked at is not regular.
Yeah. Because if we copy and paste the proof from the first one down to here, it would still work. So if we happen to not know that the first one was regular or not, then we would know the second one is not regular, or the other way. Yeah. The order does matter here. If you know one of the things on the left is regular, then if the one on the other one on the left is also regular, then the one on the right must be regular by closure under intersection. But if you know that the result, the thing on the right, is not regular, like you've already proved it, there's no way the thing on the left could have been regular because of closure.
You're talking about like 0 star, 1 star, not like the right by L2, in this instance, the right of the 0, 1 star.
Yeah,
Left
the left side is L1 intersects 0 star 1 star. So 0 star 1 star is always regular. We already know that for sure. If L1 is regular, then closure under intersection tells us L2 is regular. But if we prove that L2 is already not regular, there's no possible way that L1 could have been regular. Because if it were, then L2 would have been. Okay? Does that make sense?
Oh, so
Yeah.
L1 or the 0 star, 1 star.
What?
L2 is
Yeah,
regular.
but we already know for sure 0 star 1 star is regular. It's not like an if condition there. Yeah. Other questions? Okay. If there are no questions, I want to show you hopefully two examples that are really cool. So these two are my favorite non-regular languages to prove. So L3, it's going to be not zeros and ones, but only zeros in this case, but a perfect square number of them. So the exponents get a little weird here. The 2 on the n actually does mean n times n. The n squared on top of the 0 means n squared copies of 0. So the exponents are kind of weird. But the idea is here, perfect square number of zeros. So for example, the empty string's in there, zeros in there, 4 zeros are in there, 9 zeros, and so on. And you can start seeing a pattern and get some intuition as to why this is not regular, because each successive perfect square gets further and further apart from the last one. So there's no repetitious behavior. That's not a proof, but it's an intuitive idea. So I want to claim L3 is not regular. So we could either prove this via direct proof via the pumping lemma, or a flawed intersection example. But which one do you think would be more applicable here, considering the languages we've seen so far? Pumping lemma, yeah, because we're dealing with strings with zeros and ones, and this one only has zeros in it. And actually, this language is completely disjoint for the most part from the other two languages anyway. So, so then let's do a standard pumping lemma style proof. So assume L3 is regular. And that tells me what? There exists a P for L3. So I just remove the words pumping constant. It's not necessary. I just say exists a P for L3. Then what do we need to do? Yeah, choose a string with what properties? It's in the language and length at least P. Any choice. 0 to the P squared. Will you let me pick that? It's way more than P. Yeah, it has to have length at least P. So let's pick 0 to the P squared. So this is one, unlike the previous two, where any value of I will work. But here, it's it's medium difficulty to prove for one particular I, and I'm not sure about other values of I. So I'm going to pick the value of I this time. But before we get there, what is the decomposition of this string? What is X going to contain? It's going to have zeros. Could I have anything else? No, the whole string zeros. All right, so that's good. So X is going to be some number of zeros, and the number of zeros is not going to matter in this case. For X, I mean. Y has some number of zeros, let's say B again. B is at least 1. And Z is how many zeros? P squared minus A minus B. Coolio. So what do I need to, or what do we need to do next? Choose a value of I and hope what? It's not in the language. It's not a perfect square number of zeros. Okay, so we're going to choose I equals 2. So what is x, y squared, z? How many zeros am I going to have once all the dust settles? How many zeros am I going to have for x, y squared, z? Well, the p squared is not going away. P squared plus b. Because I have an extra copy of y in there. So I'm going to put in another b zeros in there. Can you tell me whether or not p squared plus b is a perfect square or not? You sure?
I mean, it might be.
Might be.
If B is a
We'll get to that. Well, if it is a perfect square, I shouldn't pick this value of I, right? Let's see. What could we do? Well, maybe what we can try is to see if it's between two consecutive perfect squares and not equal to either one. What can I say? It's not a perfect square. Well, let's look at this value, p squared plus b. And then maybe, let's see how high it could possibly be and how low it could be. Well, what is the lowest that it could be? P squared plus 1. Why? B can't be 0. It has to be at least 1. Oh, is there a perfect square right around p squared plus 1? P squared. Can p squared and p squared plus 1 ever be equal? Nope. So it's not equal to that perfect square, so that's good. But that doesn't preclude it to not equal some other perfect square somewhere else, some higher one maybe. What is the next perfect square after p squared? P plus 1 squared. Let's figure out what that is. So let's break out our 3rd grade algebra and let's figure, so what is this? P squared plus 2p plus 1. Well, that may be, it still may be equal to that. We haven't proven that yet. Well, how high could p squared plus b be? Unfortunate choice of name, but how high could it go? Well, is p fixed? Yes or no?
Yes.
Yes, because we assume that that constant exists. The thing that changes is b. So how high could b possibly go? Well, it could be up to that point, but what is the length of xy at most? P. What is the length of y at most? P. Because x could be the empty string. I never said it couldn't be. Oh, so that must mean that this is at most p squared plus p. Oh, could p squared plus p and 2p plus 1 ever be equal? Even if p were 0, which it can't be, even if it were 0, this plus 1 gets us. So let's recap. This is the length of the string that we got, and we proved it can't be less than this thing, p squared plus 1, can't be more than p squared plus p. It's somewhere in between those two, and we have 2 consecutive perfect squares right outside that range. So what can I conclude? It's not a perfect square. Is not a perfect square. And therefore, L3 is not regular. Yeah?
What's the comparison that you did with p squared plus p and p squared plus 2p plus 1?
Well, it's a strict, and it's definitely an inequality because there's more p's and there's more 1's in there. But this plus 1 will always get us. It is a strict inequality. Okay? Yeah, the plus 1 will always win. Yeah. What part? Well, this is the length of the string that we got. We know it's at least this value and at most this value. There's a perfect square right outside over here and a perfect square right out over here. Can there ever be a perfect square in between those two? No, they're consecutive perfect squares. Okay? There's none in the middle. So it can't ever be equal to a perfect square because we have a strict inequality on both sides. Yeah?
How did you go through the process of how you got p squared plus p again?
Because, well, how high could the length of y possibly be? Well, I know as a stipulation of the lemma, xy has length at most p.
So why can't have a
Yeah. Yeah.
Okay.
Yeah. Mm-hmm.
So x and y is like greater than p right now, or
No, xy's length is at most p, always, always. This is the length of the string that I get. Yeah, so yeah, this is the length of the resulting string.
which is greater than p?
I'm not. I don't really care about the length of the resulting string. I care about whether or not that it's a perfect square or not. That's the thing I care about. Other questions? So this tells us something interesting. I can't ever build a DFA to verify correctness of a program that computes a perfect square, because if it could, then it can figure out whether an input is a perfect square or not. But we just proved it can't. So DFAs are really limited. You have a question?
Yeah, so your exponents are summed because you chose y equal 2, and that expression x, y
Yes. Yeah. Yeah, so a plus 2b plus p squared minus a minus b equal, when all the dust settles, p squared plus b.
That can't be true because y has to be.
It has length at most p. Yeah, it could have length p. I don't know, but I'm just saying it has length at most p. Yeah. So I'm handling every possible case here. Other questions?
I have a question.
Yeah.
So we know that b squared plus b, the least we can be is b squared plus 1.
Mhm.
We know b can also be
Yep.
0.
Mhm.
And we know that that is greater than b squared. But then how do
Yep.
we know, because we said it's consecutive factor squared, right?
Mhm.
So how do you know that that's not a factor squared from
Because, or is there any square between p squared and p plus 1 squared? No, but p plus 1 squared is that last condition, last part. So there's a strict inequality here on both sides. So it can't be equal to either one of them. And we know that there is no perfect square in the middle somewhere. Yeah. Other questions? Yeah.
How do we know p squared plus b is less than p plus 1 squared?
Because of this plus 1 right here. This plus 1 will always get you. Even if p were 0, which it can't be. But if it were, then that plus 1 will still get you. Yeah.
So are we assuming that b in that whole inequality is not b?
Uh,
So like say that it's
B is this varying thing based on the decomposition. It could be anything, according to the stipulations.
Well, you said b has to be greater than
At least one, yeah, for sure.
1.
Yeah, but it's based on the decomposition, and we're handling all decompositions here. But I'm just looking at a particular decomposition, and then since these values are arbitrary, then this handles for every decomposition all at once.
so we just have to find one case where
Yeah, and here, sometimes you do need more than one case, depending on what string you happen to pick. But since it's all the same character, they're all the same decomposition. Yeah.
Just so I understand what exactly we did here, we got the p squared plus b, which is at least p squared plus 1, which is strictly more than p squared, which is the next smaller square.
Yeah.
And then p plus 1 squared is the next perfect square,
Mhm.
and b at most could be p. So p squared plus p is strictly less than
Yeah.
p plus 1 squared.
Yeah, so there's no way it could be equal to either. Other questions?
So if it was equal to either, it could be a perfect square.
Yeah, it could be, but we proved it can't be
Okay.
in all
Because
decompositions.
B can't be 1.
It can't be 0.
It can't be 0.
Yeah. Other questions? So let's do one more if we have time for it. So this one will really warp your mind. If we don't finish it, I'll leave you to think about it. So 0 to p, where p is prime.
It's not regular because it's saying
And I claim L4 is not regular either. If it were regular, then all modern cryptography would break. Because then I can figure out in linear time whether a number is prime or not. But it's not regular, and it's actually a very difficult language, this particular language. So thank goodness for modern crypto. But I claim it's not regular. So how do I start? Assume it's regular. Then we know there exists a P for L4. What do I do next? Pick a string. All right. So choose W equals, so I'm going to suggest a string. 0 to the P. P stands for prime, so therefore it's in the language and has length at least P. Is that right reasoning? I don't know if P is prime. That's the language. I'm checking whether it's prime or not. I don't know if this particular value of p is prime. But I need to pick some prime, at least p. Can I guarantee there exists one? Yeah.
Isn't there like a formal statement like
For maths,
Not for math. How many primes are there? Infinite. Can they all infinitely many of them live less than p? Be less than p? No. So there must be at least one prime, at least p. I don't know what it is, but is there one? Yeah, so let's pick that guy. So I'm going to pick 0 to the r, where r is the smallest prime, at least p. And I'm going to make a very, very slight adjustment. And I want you to tell me if it changes anything. I want it to be at least p plus 2. Does r not exist now? Is there still a prime at least p plus 2? Yep, p plus 2 is still finite. You'll see why this plus 2 is so problematic. It's going to make us show that's not regular. Well, I know that if we look at all decompositions like we have before, then we have x equals some number of zeros, y is some number of zeros, z is some number of zeros. But here, what we're going to do is we're not going to look at x, y, and z. We're going to look at the length of the string, because there's only one character. That's all we care about anyway. So let's look at x, y to the I, z's length. Well, it's not immediately clear to me what value of I should pick. Okay? I don't know what value of I to pick. Maybe what we can do is we can go through some computation and then at the end pick the value of I, and then everything will fall through for us. Maybe that'll work. And what do we want at the end? We want this, whatever this number is, to be not prime. Because if it's not prime, then it's not in the language, and therefore the language is not regular. Good. So let's break up the string into some little components. Because what I want is, if I want to show some number's not prime, how can I convince you a number's not prime? Show you two factors that are not one or that number. So if that number is the result of multiplication of two numbers which are of both at least 2, then what can I say? They're both at least 2, that means it cannot possibly be prime. That's where the plus 2 is going to help us. So let's break this string up. So I'm going to do a series of calculations, and I want you to tell me if I'm trying to cheat here. So let's have this length. Is this equal to the length of xz plus the length of y to the I? Is that any different? Well, I just broke the string up into 2 pieces. Did I change the length? No, so that's fine. So this next one's a little bit possibly more controversial, but let's try it anyway. xz plus I times the length of y. That seems fine too, because it's just y concatenated I times. Well, what I'm just doing here is just saying I copies of y here. So I'm not changing the number here, thank goodness. So now we need to figure out what this value of I is, what we should pick. So we'll take a little bit of a detour. Well, let's see. The length of x, y, z is at least what? P plus 2, by definition. What is the length of xz at least? Well, how high could y possibly get? P. Well, if I took p characters away from p plus 2 characters, how many do I have? 2. That's where the 2 is going to help us. So I want some number that is at least 2 multiplied by something else that's at least 2. Well, let's see. If I have the length of xz, that's something that's at least 2. So maybe I want that multiplied by something else at least 2. What do we know about the length of y? It's at least 1. It's at least 1. How do I make something that's at least 1 be something that's at least 2? What do I have to add to it? 1. Add 1. Because it's at least 1. Why don't I just add 1 to it? Well, this clearly is something that's at least 2. And this is something else at least 2. Well, that number's not prime. What value of I did I pick? If I expand that out, what do I get? The length of xc plus length of xc times the length of y. Could I choose I to be the length of xc? Yeah. Did anything mandate that I had to pick the same value of I for all decompositions? No. So this is an important thing. You do not have to pick the same value of I for all decompositions. You have to pick some value of I for each individual decomposition. They could all be the same. They could all be different, and like in the case here. But as long as I pick some finite value, I'm good. Yeah.
What's on the other side of the equals, just above the 2 sign? Like, yeah, on the left side of that.
Oh, this line over here, you mean? Or do you mean the one down here?
Yeah, the one.
Yeah, well, so what about it? What, yeah, so this, this comes down here. I was taking a little detour so that we could figure out what thing we want to be at least 2 and what thing do we want to be not at least 2. Well, yeah, that's an important point. You can, all you have to do is pick some value of I. Well, is the length of xz finite and at least 0? Yeah, certainly. So therefore, I'm good in doing this. Okay? So this cannot possibly be a prime. Because it's the product of 2 things which are both at least 2, and then therefore L4 is not regular.
Product of 2 things at least 2 is not prime.
Yeah. That's why I needed the plus 2 over here. Because if I had plus 1, then I can only guarantee the length of xz to be at least 1, and I can't guarantee it. It's pretty slick, isn't it? But I don't expect you to do that on a test or on a homework or whatever, but it's a neat trick in figuring out and actually showing a lot of cool things. Something that people really care about, and to show that you do not have to pick the same value of I all the time. Any questions before we break?
The choose I in the length of xc,
Yes.
which is that just to
Yeah, we chose it to make it work. Yeah, as long as I pick some value of I, it works.
So there's like 3 ways to hijack pumping armor. You said by relation,
By intersection, yeah. And
what's next?
it's really a standard application of the pumping lemma,
Okay.
but it's just picking the value of I that works. Instead of picking I up front, you pick the one that works.
And then brute forcing it by.
Yeah. So that was like the only one that could have worked here. Yeah.
Okay, thanks, man.
Yep.